All right. Hey team. So today we're doing a quick overview of unsupervised learning. And I'm going to talk about this in relation to how you can utilize this for your EDA, because I think most people's projects this time around are not using unsupervised learning as the main bulk of their projects. So I'll talk about this combination of both clustering as well as using dimensionality reduction as well. So to start, just to recap, back to basics, unsupervised learning versus supervised learning. The main thing that distinguishes between the two is that in supervised learning, you have some sort of Y variable that you're predicting, either doing classification or regression. Those are the most common types of supervised learning, and your data is labeled. The Y variable pretty much are your labels. Unsupervised learning, as we know, does not include labels. You're either doing something independent of how your target is distributed, or you're forming groups or such. So I'm going to talk about clustering real quick first. Clustering, we know, and we're going to go more into clustering in a little bit, but clustering, we form groups based on the distribution of your numerical data that we already know. Two main techniques of doing that. Two main hard clustering techniques that we talked about back at the start of phase 4. We had our k-means clustering and we had our HAC clustering. One is pretty much top down, one is bottom up. So we'll get more into that in a little bit. But first, let's talk about dimensionality reduction. So PCA is one of many algorithms that reduce dimensionality. Couple of reasons to use PCA. First, let's start with visualizations. Turning your data into 2D or 3D just so you can visualize. Actually, let me pull up the PCA slides up real quick so we can take a look at an example. So if you're doing something like classification, I think classification is actually a really good time that you could consider using PCA for visualizations, because you want to see the separability of your data, right? So if you were to lower the dimensionality of all of your X features into 2 or 3D, so in this case, this is 3D, if you're going to lower the dimensionality of that and then plot your different scatter points in different colors, you can sort of get a sense of the separability of your data. For example, here, I mean, it does look like there's some overlap, but there are some distinctively red zones and some distinctively blue zones. And so that is a sign of separability in your data. And I remember with this data set, I actually managed to get like a 98% on classification. And that those clear zones of red and blue are very likely why that is. So PCA for visualizations, also always a good idea. You don't necessarily have to use PCA. Actually, let me go back to here. There are a couple different methods, if you remember from what we talked about at the beginning of phase 4. PCA is good for dense, continuous data. So if most of your features are continuous, you don't have too many zeros, so you don't have a very sparse matrix, regular PCA works fine. And by the way, the syntax for all of these very, very similar. You just do your fit, transform, and chain, transfer, run test. If your data is more sparse, perhaps you're using text data, image data, something that has a lot of dummy variables, you could use truncated SVD. It's just more efficient in computing the lower dimensions. So truncated SVD is good. And I actually didn't use t-SNE for this, but t-SNE kind of optimizes for the separability between your points. As a very, very quick one-line refresher, PCA tries to optimize for overall variance in your data. t-SNE is looking for separation. So they're kind of similar, but different, with just slightly different. Okay, so here we have PCA for visualizations. Next, some of you might start to see this as your data sets get really, really big. You can use PCA for algorithmic efficiency. If you find that some of your models are taking very, very long to run, one method you could try is lowering the dimensionality of your data first and then run your models. So it's really just because you have fewer columns of data to look through, and because PCA is reducing the number of columns while maintaining the variance in your data, the important variations in your data will be kept or will be maintained with PCA. So remember that for PCA, the output is principal components, and every principal component is a linear combination of every original feature. So if you started with 10 features and lowered it down to 2 dimensions, PC1 could be something like this, like 0.1 times feature 1 plus 0.2 times feature 2, so on and so forth, all the way to feature 10. PC2 would be exactly the same, but just with a different balance of coefficients. So features with low coefficients are usually less important or have less variance overall. So for example, if I'm trying to classify a data set into 3 different groups, and I have this one feature that pretty much only has one value for every single row, that feature will probably have a coefficient of probably very close to 0 because it does not have much variance in its values. Again, one downside of PCA is you lose that interpretability. If you were to do PCA and then you take a look at your feature importances from like a random forest, for example, your importances are going to show, okay, feature or principal component number 5, 6, and 7 are the most important. So from that, you lose that one level of interpretability. However, you can figure out what they are. Well, actually, where's my PCA documentation? You can actually go into each principal component to see the makeup of each principal component. So as an example, not as an example, but as what you want to find is the components. So because the array will be of n components and features, let's just say your most important feature was PC number 5. You can actually go into PC5 and figure out what the coefficients are for PC5's version of this. And maybe you can get a little bit more of a sense of which feature is actually important. So PCA is useful for that as well. So we've talked about that. Cool. So PCA on text. A lot of you are doing NLP projects, and because you lower you lose interpretability when you use PCA, I do recommend lowering dimensionality using the vectorizes parameters instead of using PCA. I'm going to talk a little bit more about this tomorrow, but if you're doing a NLP project and you find that you have a lot of columns and it's taking very, very long for your model to, fit, instead of doing something like PCA where you lose information or lose interpretability, in account vectorizer or TF-IDF, and I'm going to talk a little bit more about this tomorrow, you can actually lower dimensionality through your vectorizer, where instead of removing or instead of making principal components, you actually take away words that are not important at all. And the way you can do that, and this is actually something you can tune with grid search as well. I don't remember if I mentioned this when we first saw this, but one thing that you can do is, where is it? Max DF, or there's max features as well. So here, you can actually set a max features within your count vectorizer so that you don't have those like random words that only appear like once or twice. By doing that, it actually orders it by term frequency across the corpus, and then it cuts down dimensionality in a more interpretable way. So this is a good one too. Any questions so far? All right, so Teasney talked about this earlier, better for visualizations because it tries to maintain or tries to create more separability in your data. But I think regardless, if you have like thousands and thousands of columns that you're trying to lower into 2 or 3 dimensions for visualization, it's not a big difference what you'll see between Teasney and PCA. So honestly, for visualizations, either one will work. Teasney does take a very, very long time to train, so I'll warn you of that. Okay, so that's reducing dimensionality. Really useful for EDA. I think especially if you're doing some sort of classification problem or regression problem even, plotting all of your aggregated data or your aggregated columns together and showing the relationship overall is a pretty neat visualization. Okay, so next to clustering, and we're going to talk not so in depth with how clustering works, because we already kind of know roughly how clustering works, but more of how you can use clustering for EDA, as well as how you can pick clusters or possibly use it to as extensions to your project. So we have hard and soft clustering. The main difference between that is hard clustering assigns one single cluster to every single data point, whereas in soft clustering, you get kind of proportions, or you have probabilities of, okay, this data point A is roughly 50% cluster 1, 25% cluster 2, 25% cluster 3. That's the big difference between hard and soft clustering. So with hard clustering, we have these 2 algorithms. Of course, there are others, but these are the main 2 that we talked about and the main 2 that are used in practice. and because it's hard clustering, each data point is assigned to a single cluster. K-means is a little bit more random. If you remember, K-means is the one where we instantiate it at we instantiate our cluster centers at however many data points are just randomly chosen, and then your clusters will move and shift. Actually, since we have time, we can pull it up. Let's see, I think I have it over here. And we have the GIF that I hope will load. Here we go. So this is K-means clustering. It starts here, and then your clusters will slowly adjust based on new cluster centers. So it's going to keep doing that, and your results can differ depending on where it starts to choose its centers. The scikit-learn version of K-means actually has an algorithm for picking optimal centers, but you will see different results every time you rerun. The results are not going to be massively different unless your data set is wild, but typically you see that sometimes a couple of the fringe data points might end up in different clusters. So HAC is kind of different. HAC, instead of doing this method where it keeps shifting, HAC is the one that uses a dendrogram, where it does similarity metrics over all of your data points in your data set, and then combines them to form groups. So depending on the number of clusters that you want, you stop the reforming of groups, because you can kind of repeat this process over and over until you end up with one massive cluster. So HAC takes a little bit longer to run because it's computing a lot more similarity metrics versus K-means, which is just computing distances between centers and every data point. But yeah, HAC takes a little bit longer to run, but it's also more bottom up, and also the clusters never change unless your data changes, but you should change your data. All right, so with that, let's first talk about soft clustering, which is LDA, and I think will be most relevant especially for you all who are doing NLP projects. So LDA is used for topic modeling. So you can actually run either K-means or HAC on your text data absolutely fine. You can do it on you should do it on vectorized data. So either if you used count vectorizer, TF-IDF, or Spacey, just throw that data into K-means or HAC, that'll work. However, LDA specifically uses GenSim to do topic modeling. So instead of trying to group words based on their vectorized mathematical space, you're grouping it based on things that they're talking about and words that are similar to each other in meaning. So LDA is much more, I guess, you get a lot more bang for your buck if you were to do LDA on your text data. And I think LDA is a really, really good tool for understanding the things that you're talking about within your data set, especially in your text data set. If you take a bunch of tweets, for example, and then you throw like 10,000 tweets into your LDA model, it'll tell you what the main things people are talking about. If you're talking about COVID, are people talking about things like vaccines, maybe government, perhaps regulation, mandates, things like that. And you could potentially see that represented in space. And it's a really, really great EDA tool because it will tell you literally what the main things people are talking about within your data set. I do have the code for running LDA also over in the repo over here. It is taken from a different source, which I think I cited over there if you want to see that. But yeah, you basically have to do a little bit of data setup, a little bit of model setup for the LDA. It takes a little bit of time to run as well. You tell it how many topics you want to look for, and then you can just run your LDA model, and it basically shows you the, if you remember that, that interactive thing. Actually, let me pull it up. LDA for topic modeling. Let's see if there's an example here. Oops. It'll give you, all right, let's look for this PyLDA quiz. There we go. I'm just going to show you all these images, but I'll show you the thing that looks like this, where you have your different topics represented in principal component space, and then you can see your relevant terms. Again, like the main topics, and for clustering as well, for hard clustering as well, the results of what you want to label each topic is very much up to you. It's up to you to look at these words and be like, okay, based on these words, I'm going to call this topic the topic on talking about mask mandates as an example. So it's up to you to go in and label these. Now, Doing clustering and topic modeling can also be something that you can use to create additional features for your data set. So if you wanted to, let's say you have all of your words and you did a TF-IDF on it, but if you're doing TF-IDF, it doesn't really take into account too much context. And if you don't want to add like another 100 or 300 features to your data set with Spacie, you can actually do topic modeling first, and then just have maybe like 3 or 4 new features saying whether it's related to topic 1, 2, 3, or 4. That could be something that you do as well. And maybe it'll be an important feature, who knows? So doing clustering or topic modeling is clustering, but doing any sort of clustering can help you create features for your data set. Cool. So quick applications of clustering. Don't forget to scale your data before you cluster. It's important to do that because this is more for the hard clustering methods, not the topic modeling, but because clustering is done based on similarity and distance, it's important that you're measuring each feature evenly, unless you know that you want it to emphasize or not emphasize, unless you want your model to, let's say you have a bunch of keywords that you really want your model to prioritize, you can reweight those features a little bit higher or lower. So, but for the most part, you should scale your data such that most of your features will be measured on an even playing field. In determining the number of clusters, it's a very, very subjective thing. It really depends on what your business problem is, what you're actually using clusters for. So for example, here I wrote that it might be constrained by your business problem. You have no choice but to stick with a certain number of clusters. This could be the case for, let's say you wanted to create 3, or let's say you're a marketing firm and you wanted to do market segmentation. That's actually one of the big applications of clustering. In doing market segmentation, your marketing team only has budget to do, let's say, 5 different marketing campaigns. Therefore, you only want to group all of your, your data points into 5 different clusters, and you're kind of constrained by that. There are also metrics for determining the best number of clusters. We talked about a couple of these: elbow curve, silhouette score. Elbow curve is the one that talks about within cluster sum of squares, if you remember what that is. But basically, you can be very flexible because sometimes it's not very, very clear that what number of clusters is best, but you do have a lot of freedom to decide how you want to cluster your data. The most common example I will use is that I used to talk about this is I had a student that wanted to cluster different basketball players, and he was like, I got to choose between 3 clusters or 7 clusters. And then so what I did was I advised them, do you want to have 3 groups of players or 7 groups of players? Does it make sense to have less variety in the clusters or more variety in clusters? I forget which one he picked, but you are able to make that decision as long as you're able to justify why you're choosing a certain number of clusters. If it recommends 8 clusters, but you think that for whatever your business case is, you need to do 10, just say why that is, and that usually is okay. Okay. Next, again, about clustering text. LDA, as I mentioned before, will help you answer what the main topics this data set of text is talking about. You can actually split up your LDA and do LDA on segments of your text. So let's say you're doing sentiment analysis and you have a bunch of positive labels and a bunch of negative labels. You can do LDA on your positive and negative text separately to see what the things are that people are talking about within your positive group and within your negative group. And you can get a lot of useful information out of that, because sometimes just based on word count is not, and if you're just looking at word clouds, it's not immediately obvious what people are talking about. Can also be biased by if there's just a massive amount of people talking about, I don't know, what was that data set? Talking about how bad Google Circles was, for example. The other relevant topics might be overshadowed by that within a word cloud. So doing LDA for that, very, very useful. Okay. This is a quick step-by-step, I guess, of talking about creating labels through hard or soft clustering methods. Once you cluster your data, do some post-clustering EDA to label your clusters. If it's not immediately obvious, you might have to look into the data distribution within each cluster for you to be able to say, okay, this cluster is going to be players who have characteristics ABC. This group of clusters, this cluster will be people who have characteristics D, E, F. Just an example. So you have to look into those to help you label your cluster if it's not immediately obvious. And then using a dot predict will literally just give you the labels of your clusters. And you can essentially use that as a feature, maybe use that as a target variable to run through your machine learning models through as well. But yeah, I think that's it with clustering. Does anyone have any questions? I do think that clustering is a very, very useful thing to use in your project. I would say that it is one of the more analysis or analytical things that you can do with your data set, because you're trying to learn more and infer from your data based on the relationships between your data points. So if you're able to interpret things like that, I think that's really, really beneficial. But yeah, any questions on that? If not, I'll stop the recording and I'll hang on here for the rest of the hour, same as last week. Going once, going twice. All right, let me stop the recording here.